All right, on to number 2. We're going to talk today about strong acids and bases. This isn't terribly long, but we've got some stuff about conjugate acids and bases. It's a little bit complex at the end, so make sure you write some stuff down. All right. We have strong acids versus weak acids. We've talked about these before. Strong acids completely dissociate in water, and weak acids do not. The gentleman who did your video on strong electrolytes talked about that. Okay, so for example, here we have hydrochloric acid, and we'll notice if we just look at one of these guys, you'll notice we have the hydrogen, which is the smaller thing, which is the gray one, and chlorine, which is this one. All right, and they completely dissociate. So you'll notice we've got hydrogen over here and we've got chlorine over there, and they've completely separated in the water. That's what hydrochloric acid does. It essentially dissociates at virtually 100%, and so it is a very, very, very strong acid. Okay, so we write this as HCl, which is a gas. When you put it into water, well, you're adding it to water, right? What happens is it completely dissociates into hydrogen and to chlorine, and they're aqueous. They're dissolved in water. Now, we do have some strong acids you have to memorize, so please make sure you write these down. Pause the video and write them down. Hydrochloric acid, nitric acid, and sulfuric acid are very common, and they're very, very strong, which means that they all dissociate completely in water. So hydrochloric acid, we were talking about, could be pool acid, for example. Nitric acid is really dangerous stuff. And sulfuric acid, you'll find in batteries. Now, there are 3 uncommon strong acids. This is perchloric acid, and hydrobromic acid, and hydroiodic acid. And they are strong as well, but they're very uncommon because they're expensive. Right? So we don't tend to see them. Right? And it's not something that we tend to have a lot of in the lab, but we would have the first 3 in the lab. Okay, strong acids are strong electrolytes. Again, you saw that in the previous podcast. Now, we also have weak electrolytes and weak acids, which are things like acetic acid. So again, let's think let's use the same kind of logic, where hydrogen is the small thing and this green thing is the C2H3O2. All right, we're just going to call it a thing. That's your negative ion. But when it gets into water, you'll notice most of them stay together. And we only have one that's separated into the hydrogen ion and the acetate ion, and all the rest have stayed together. And what really happens in a weak acid is you have a very small amount that dissociates, only 1% to 5%. Some are even less than 1%. So it depends on what the acid is, but virtually all of your weak acids have a very, very low dissociation rate. So when we draw that, you'll notice the one thing that we have drawn that is different in this than what we have drawn in our one with HCl is this arrow, which is going in both directions. Because what's happening is if something does dissociate, something else reassociates. So in this example, this dissociated, so that's fine. So you've got 1 or 2% or 5% dissociation. If one of these others dissociated, then maybe these two are going to get back together. Or this one will get together with the hydrogen ion of that one. But you will have a very, very low dissociation rate, okay, because it actually goes in both directions. This is called equilibrium, and we'll talk about equilibrium in a future podcast, not in this unit. But it actually goes, the reaction goes in both directions. So weak acids are weak electrolytes because they don't completely dissociate. Now, we have the same thing in bases. Strong bases completely dissociate in water. Weak bases do not. So all the logic remains the same. Everything remains the same for weak bases versus strong bases. We do have 2 strong bases. Again, you need to memorize these that are very common. And in fact, it's very easy to figure out what they are. You'll notice that all the weak bases, and you've got common ones and you've got uncommon ones, but you'll notice that all the weak bases, the metal, that thing right there, the metal, is in column 1. So sodium hydroxide and potassium hydroxide, the alkali metals are sodium and potassium, are very strong bases. Now the rest are strong bases as well. The problem is they're so expensive and so uncommon that you will not see them in the lab. Right? But the 2 that we use all the time are sodium hydroxide and potassium hydroxide. All other bases, for all intents and purposes, are considered weak. And we know that strong bases are strong electrolytes and weak bases are weak electrolytes. So, how do we draw these? Well, similarly, we have a strong one, which is sodium hydroxide, and when it's dissolved in water, it becomes sodium plus and OH minus. They completely dissociate. Where you have a weak one, which is calcium hydroxide, and it actually goes in both directions. So you'll notice you have a solid here. These are going, some are dissolving, but most are not. All right, again, calcium hydroxide does not dissolve well in water. So you do not get a strong base, you get a very weak base. Right, ammonia is another example of a weak base. And bases that contain nitrogen are called amines. So how is this a base? Well, let's look at what happens. The hydrogen from the water will come over, and it will come over here to the NH3, and it will form an ammonium ion. That's one of the ones you had to memorize off your ion chart, NH4 with a positive charge, which leaves behind an OH with a negative charge. So it is producing a base. There's hydroxide in the water that is a base. So that is how you know you have a base. All right, now you have something called conjugate acids. All right, well, let's think about what happens first as this reaction goes to the right. Well, because we are producing, we have something called a proton acceptor. Remember that an acid is considered a proton acceptor. That's wrong. An acid is considered a proton donor. Like HCl would be considered a proton donor because it gives you an H. And a base would be considered a proton acceptor. Okay, so that said, if you have something like ammonia, what's happening with ammonia? Well, ammonia is accepting a hydrogen, right? So we're adding a hydrogen to go from ammonia to go to NH4. So since we're accepting it, then this must be a base. And water is giving up its hydrogen, all right? So this becomes a proton donor. So in fact, in this particular case where you've got ammonia in water, water is acting as an acid because it's donating a proton. Well, we know that water is neutral, but in this case, because we put ammonia in the water, it is donating, the water is acting as an acid because it is donating a proton to the ammonia so it can become ammonium. But what happens if we have this, which is a liquid, and it's heated? Well, when we do this, remember that ammonia is a gas. So when we heat water, what happens to the concentration of a gas? Well, in the last unit, you learned that when you have a gas in water and you heat the water, the gas comes out of solution. So the NH3 is going to come out of solution. So what's going to happen to this H, because it's an NH4? Well, the H is going to go back to the water, so this reaction is going to go backwards because we're going to produce water and we're going to produce ammonia. So what is this NH4 doing? Well, when we put the reaction going backwards, the NH4 is acting as an acid because it's a proton donor. So we call this thing a conjugate, J-U-G-A-T-E. We call it a conjugate acid because it is donating. When you reverse the equation, you are donating a hydrogen to the reaction. Similarly, this is accepting the hydrogen, so it is going to be a conjugate base. All right, so that's what happens if we take the reaction in the reverse direction. So we have a pair. We have NH3, which on the left is considered a base, and it's becoming NH4. So we have a conjugate acid-base pair, and that is NH3 to NH4. That's considered a conjugate acid-base pair, and we have water and OH, which is considered a conjugate acid-base pair. All right, let's do a couple so that you can see how that works. Right. Let's come up with a formal definition for a conjugate acid. A conjugate acid is the particle formed when a base gains a hydrogen ion. The particle formed when a base gains a hydrogen ion. So if NH3 is the base and it gains a hydrogen ion, then it's becoming NH4. So that is going to be your conjugate acid because NH3 became NH4 because it gained a proton. It gained a hydrogen ion. Okay? Now, how about your conjugate base? Well, your conjugate base is the particle that remains when an acid has donated a hydrogen ion. When it's donated one, then it becomes a conjugate base. So water, which was our acid in this case, donated a hydrogen, and what's left is the OH, so it's considered the conjugate base. And the conjugate acid-base pair are two substances related by the loss or gain of a single hydrogen ion. Guys, write that down. Pause the video, make sure you write that down. It's important that it is a single hydrogen ion. And that can be very confusing, especially if you're dealing with a diprotic acid. All right, so let's look again at this conjugate acid and base. Without going back to the previous, your previous notes where you wrote this down, can you figure out which one's the acid, which one's the base? Okay, did you pause the video and do that? If not, please try. All right, well, NH3 is, well, as it goes over to NH4, it is gaining, it is a proton acceptor. If it's a proton acceptor, and guys, think of it something like HCl and NaOH, right? What's happening? Hydrogen is donating a proton. This is going to accept it because it's going to become HOH, right? So the OH is accepting, right? So this is your base. I kind of just think about it that way, right? So the NH3 is accepting. It's a proton acceptor. All right, so that means it is a base. That means this thing over here must be the conjugate, and it's the conjugate acid. Because if you reverse the direction of the equation, it is acting like an acid. Similarly, the water over on the left must be acting, because it is giving up, it's a donor of a proton, so it must be an acid. Hence, this must be the conjugate base over here. Right? How about this one? Pause the video, see if you can figure it out. Well, let's look at what is clearly happening here. We have water, which is becoming H3O. So this is an acceptor, which means it must be acting as a base, right? Because it's accepting an electron, it's accepting a proton. So that means this, if we reverse the reaction, would be donating it right back, right? So it would be a donor. So this is the conjugate acid. Similarly, here we have HCl, and that's donating the hydrogen. So that must be an acid. And of course, we do know that HCl is an acid. There's really no question there. So that means the chlorine must be the conjugate base, because that's what's left over after it has donated the proton. All right. Now, typically, when we think of sulfuric acid is a strong acid. So sulfuric acid, when we put it in water, will completely dissociate, and we get SO4 with a 2- charge, and we get 2 H+ ions, or 2 hydronium ions if you want. You can do it either way. All right. So over here we have our acid, and the water is acting as a base. Right. So what's actually happening with conjugate acids and conjugate bases? And this is why I said you had to be careful with, because if you remember the definition, it said you're dealing with a single proton, a single hydrogen ion. So H2SO4 is clearly an acid, and if it gives up a single hydrogen, we're creating one H3O. So this is our conjugate. That's our conjugate base. Did I do that right? I always hate it when I do that. That's my conjugate acid. Now, what happened? What's left? You only lost one hydrogen ion. So you've got an HSO4 with a -1 charge. Now, in reality, that doesn't happen very often. In fact, it only happens for a moment in time, because what's immediately going to happen is that HSO4 is immediately going to lose another hydrogen ion to give up another H3O, so that you're finally left with SO4 with a -2, like we see up here. All right. So our acid up here loses one electron, and the water over here gains one. So that would be an acceptor, right? So that becomes the conjugate base. I'm sorry, that is a base. Our HSO4, which is what lost an electron, which if we reverse the direction would be gaining. All right, So that would mean this must be the conjugate base. And the line below would be exactly the same. All right, that's it for conjugate acids and conjugate bases. If you need some more examples, please see me in class, or please see one of us in class. We'll be happy to help you. Okay, that's it. Hope you have a great day. We'll see you in class.